Hello, welcome to problem solving session for computational commutative algebra. I am Siddhi Balwambure from IIT Gandhinagar, and today we will discuss problems related to the syllabus from week 1, that is problems related to ring homomorphism, quotient rings, Noetherian rings, and monomials. Okay, so we will start with our first question. And if you have any doubt, please feel free to unmute yourself and ask. Otherwise, if you don't want to unmute yourself, then you can just write your questions in the chat. But feel free to ask your questions. So let us start with our first question. So question 1. And please let me know if I'm going too fast or too slow so that we can adjust the lecture accordingly. So let us start. So let R and S be commutative ring with multiplicative identity. So since this is the first time I am writing this, so R and S, so whatever rings which we will be considering in this lecture or this live session will be commutative rings with the unity or multiplicative identity, as you say. So R and S are two rings, commutative rings with the multiplicative identity. And so let F be a ring homomorphism from R to S. Then we have to pick the correct statements. So there could be one or multiple from the below. Okay, so the first option is that image of F is an ideal of S. So image F is what? Image F is this set. It is set of elements in S such that B is F of A for some A in R. Okay, so this is my image F. And second option is that kernel F is an ideal of R. Okay, and what is kernel F? So kernel F is all those element A in R such that F of A is 0. Okay, this 0s is 0 in my codomain ring S. Okay, and my third option is that kernel F is a subring of R. And last option is that if F is bijective, then this image F is kernel of F inverse. So F is bijective, so F inverse exists. And what they are saying that this image F is kernel of F inverse. Okay, so any guesses for this? So this is okay, B and C. So guesses are B and C. So let me mark them with the green for now. So guesses are B and C. As Subhadeep suggested, the suggested answers are B and C. So since they are saying that there could be multiple answers to this, let us first try to discard each and everything, because as we go on excluding or including each option, we will be learning many things in between. So let us start with the part A. So part A is what they want to suggest that image F is an ideal of S. So as even the guess from Subhadeep was that it is not the correct answer. So can somebody tell me an example where image F is not an ideal of my ring S? By the way, everyone knows what is ring homomorphism, right? So If not, then let me just quickly define what is ring homomorphism if you don't know or if you couldn't go through the lectures. Let RNS be rings, Z to Q inclusion. Yeah, this is correct. Okay, but let me just quickly go through this definition. A function f from R to S is ring homomorphism if first one is that f of R plus R dash is f of R plus f of R dash for all R comma R dash in R. Second property is f of R dash, R into R dash. So now this is multiplication. So this is f of R into f of R dash for all R comma R dash in R. And third one is, since we have these rings with the unity or multiplicative identity, this f of 1R, so multiplicative identity of 1 R goes to multiplicative identity of our codomain ring 1S. Okay. So these are the three properties which are satisfied by our ring homomorphism. So they are saying that image F is our guess is that it is not an ideal of R. So of S, and as Subhadeep suggested, we can take this example F from Z, ring of integers, to ring of rational numbers, such that inclusion. So it is like A is going to A here. And what is image of F here? It is Z again, right? But is Z an ideal in Q? No, right? Because what is ideal? Yes. So what is ideal? So ideal is a set. So what is ideal? Let me just write. So let A be a subset of R. Then A is ideal of R if A is closed under addition and A into R belongs to or not. For all A in A and R in R, A into R belongs to this set A again. Okay. So this is the definition of ideal. So but if I take, so if Z is ideal in Q, then for let us take just for example 1 by 2 belongs to Q and 1 in Z, 1 by 2 into 1 must belong to Z, right? But this is not true. Okay, so therefore therefore A is wrong and this image F is not an ideal of S. Okay, any doubts here? Please feel free to unmute or ask in the chat. Otherwise, I will move further to discuss the second question, second part of this question, or B part of this. Okay, so B part, and B part is what? That kernel is an ideal of R. So we have to check that. So what we want to check, that it is closed under addition, means A plus B. Let me just write that for to check that kernel F is an ideal of R. So we have to check what? First, we have to check that for A comma B in kernel F, whether A plus B belongs to kernel F or not. And second is that for all A in kernel F and R in R, whether A into R belongs to kernel F or not. Okay, so let now A and B be in kernel F. Then what is F? Then what is F of A plus B? Since F is a ring homomorphism, it is F of A plus F of B. And which is what? Since A and B are in kernel F, it is 0 plus 0, right? Which is 0. So this implies what by definition that A plus B belongs to kernel F. Okay. And similarly, if I take any R in R and A in kernel F, then what is F of R into A? It is F of R into F of A. But what is F of A? Doesn't matter what is F of R, but what is F of A? It is 0. So 0 into any element of a ring gives me 0 again. So these zeros are in zeros of S. Okay. So this implies what? That R into A belongs to my kernel F. So both the conditions of ideal are satisfied by the elements from kernel F, and the elements which we chose were arbitrary. So this answer is indeed correct. Okay, so the guess which was made is correct. And now third is that kernel F is a subring of R. Okay, so what is definition of a subring? So the subring was not formally defined in the lecture, but it is given in the additional notes or additional non-graded PDFs which are submitted in the portal. So you can go through it. And definition for a subring. So let me go through the definition of subring. So a subset A of R is called a subring of R if it is a ring on its own with same multiplication and addition, same addition and multiplication operations as R, and same additive. So since multiplication and addition are same with respect to same as the operations in our main ring R, the additive and multiplicative identities must also coincide with the identities of our original ring R. Okay, so we want to check whether this kernel F is a subring of R or not. So now that when we say subring, it also need to have, so it's ring on its own. And for us, when is something is a ring? When it has multiplicative identity in it, right? So if kernel F is a subring of R, then what? Then one R or the same multiplicative identity as R must belong to this kernel F, right? But since F is a ring homomorphism, what is F of 1R? It is 1S, right? And which is, yes, and which is not equal to 0S. So we are not dealing with the zero ring where 1S is equal to 0S. This could be anything. These statements are made in general setup. So for in general, 1S need not be equal to 0S. For example, consider for Z itself. Okay, so in that case, this 1S is not equal to 0S. So therefore, this 1R actually doesn't belong to my kernel F, this set kernel F. Okay, so therefore, this kernel F cannot be a subring of R. So, Shubhadeep, is it clear why it is not a subring? Okay. So this one is again, this is not subring of R. And now final, if F is bijective, then image F is kernel F inverse. So any guesses? So as the earlier as suggested earlier, that fourth one, that is the D part, was not correct, right? So any guesses that we want to find a function, a ring homomorphism, in fact, such that ring homomorphism which is also bijective, such that, what is it? Image F is equal to kernel F inverse. Any guesses for this? Yes, exactly. So yes, so as Subhadeep said, since it is bijective, kernel must be 0 itself. So map is 0. So in order to have bijectiveness, the map needs to be injective. And once we have injectivity, kernel F becomes 0. Only the 0 element belongs to kernel F. So this is clearly not possible. But image F is equal to, because since it is bijective, we have to have like entire ring as its image. And now kernel of F inverse is, since it is bijective map, F is bijective, so F inverse must also be bijective map. And so this it's not, I mean, this is completely wrong, but still let me give this ring homomorphism F from Z to Z, this identity A going to A for all A in Z. And what is F inverse? F inverse is Z to Z again, same. It is actually F, if you check. It is again A going to A. And we can here see that image of this F is actually entire Z, but kernel of F inverse, which is kernel of F again, because F inverse is F, it is just my zero set or zero ideal or whatever you want to call it. And clearly Z is not equal to the singleton 0. Therefore, this statement 4 is again false. So the only statement correct here is this, the B part, that kernel F is an ideal of R. Okay. And as we saw that kernel F is not a subring, because our ring homomorphisms are such that 1 goes to 1 and 1 is not equal to 0 in general. So therefore kernel F is not subring in general. Okay, so any doubts here? If not, then we will move to next question. Okay. If you could you please scroll up once, wanted to note down definitions. Okay, so you don't have to note down everything now. So this written notes will be shared with you immediately after the lecture within 1 hour maybe. So I mean you can write down, but for now you can just take screenshot of your device and I will be sharing these notes with you. So don't worry. Is it okay? So can I move to second question for now? Okay. So let me start with the second question. Uh, so we have to, so this is question from the extra notes, which are non-graded assignment given in the our portal. And it is that show that there is a unique ring homomorphism from Z to R. This is any ring R. The characteristic, so this characteristic of R is the unique non-negative integer generating the kernel of this homomorphism. So we have to show this, that there exists unique ring homomorphism from Z to any given ring R. Okay, so since Let us call this F. So F is any ring homomorphism from Z to our ring R. So let R be any ring. When I say ring, again I'm repeating that it is commutative with the multiplicative identity. So let F be a ring homomorphism. Be a ring homomorphism. Then clearly f of 1 goes to where? So since we are in Z, I'm not writing 1 sub Z, it is just 1, or let me just write for 1, which is again our normal one. Where does it go? It goes to 1R. It goes to additive multiplicative identity of R. And then every element of Z is some integer n, which can be written as addition of 1 n times. Okay. So for a non-negative integer. So what is f of n? It is, again, since f of 1 plus up to 1, this n times, yes, n into f of 1, correct, n times, and it is what? F of 1 plus up to f of 1, and this becomes n times. So this is n into 1r, if, or it is just 1r. Let me just write this, and which can be written as n into 1r. Okay, so, and what is f of minus n? It is f of minus 1 into f of n, right? So it is minus 1r. F of minus 1 goes to f of minus 1r, okay? So with into f of n, so it is minus 1r plus minus 1r plus minus 1r. This is n times again, and which is minus n times 1r. Okay, so this is the map, and this has to be the only map defined from Z to 1R because of this condition that f of 1 goes to 1, and the moment we have f of 1 goes to 1, where this 1 in the domain is Z, then the map defines then this f of n, which is obtained by the additive property of ring homomorphisms, give me the nature of entire f, that how the f is defined. Okay, and what they are saying that then this kernel of this mat f, which is defined here, is what? By definition, such that f of n is 0R. Okay, now we earlier saw in our earlier question that kernel f is an ideal. So which is ideal in Z, right? And note that ideals in Z are generated by single integer. That is, in other words, Z is principal ideal domain. Okay, so this kernel f must be generated by some m, or similarly minus m, for some m where m is a non-negative integer. Okay, this much is fine. Any doubts so far? And now what they are saying is that this m needs to be unique. Okay, so once we said that the generator of an ideal is a non-negative integer, it becomes unique. Okay, so if it is a ideal, it is generated by either m or minus m. Okay, and the moment we say that we want to look at the generator which is non-negative, it becomes ideal generated by unique number, that is m, and this m is now called this characteristic of R is now this m, which is some non-negative integer. Okay, So this is the definition of characteristic, and also note that this map is unique the moment we have 1 goes to 1, and how the additivity property of a ring homomorphism gives us the entire nature of map F. So this map is unique, and this characteristic is a integer which generates the kernel F. And also note that this kernel F is 0 when we have map injective. So in case of injective maps, the characteristic becomes 0. Okay. Is this clear? Okay. Okay. So now we will see this next question where we have to. Okay, it's clear. Great. The find the characteristic of the ring Z mod 4Z x comma y quotiented by this y minus x square. So this is my ring. Okay, so this, let me call this ring A, and we have to find the characteristic of this ring. Any guesses? So first of all, do you understand how the elements of this ring look like? So first of all, this is quotient ring. So elements are in equivalent classes, or okay, and then they are like of the form. So this Z by 4, so A is F plus y minus x square, such that F belongs to this Z mod 4Z x comma y. Okay, these are the elements of this F, and this F is again element in Z mod 4Z xy. So it is some polynomial. So let me write it is like C alpha alpha some index set I x power alpha 1 y power alpha 2, and this C alpha finite. Okay, C alpha belongs to Z mod 4Z. So coefficients are coming from Z mod 4Z. Okay, so any guesses for the characteristic? So we also have options for here, options that A, B is 4, C is 0, and D is 3. So answer is from these 4 integers. So any guesses that what will be the, first of all, it is okay like how elements of this ring look like? Okay, so already the guess we have here is that 4. So they are saying that 4 is okay, the characteristic of this ring. So let us see how to proceed. So F we take from Z to this ring A, such that 1 goes to this 1 in this ring A. Okay, and note that first thing that when we write this, that kernel F is generated by some M element. This M is also smallest positive integer belonging to this M, belonging this to this ideal M, when this M is non-zero. Because once we have zero ideal, everything is 0. I mean, the only element belonging to that ideal is 0. So when we have non-zero ideal, it is generated by some non-zero element M, and that M is again, okay, I will repeat that. So that M becomes, that M is actually smallest ideal belonging to that ideal generated by that non-negative integer M. So what I was saying earlier, about injectivity of the map. So this F map is injective. In that case, kernel F will be just 0, right? It is if and only if condition that kernel F is 0 if and only if map F is injective. So characteristic of a ring R will be 0 when map F, this unique map from Z to ring R, is injective map. Is it okay? So let me just write it for you also. So F is injective, kernel F is just 0 element, and in this case, and this F is from Z to R. In this case, characteristic of this ring R is 0. That's this is the only thing which I said earlier. Is it okay? Because kernel F is 0 means what? It is generated by element 0, and that M, so here that non-negative M is 0. So that's it. This is what I wanted to say earlier. Is it okay? Okay. So that's it. And apart from that, in this question, what I was saying is that the least positive integer belonging to non-zero ideal generated by M is the generator of that ideal. So what I'm saying is that this M is non-zero, then M is the smallest positive integer in this ideal M. Okay, this is what I'm saying, and that's how we will be doing. So the guess is 4. So we will see where the images of 1, 2, 3, and 4 go in this ideal. So what is f of 1? F of 1 is again 1a, so which is clearly non-zero in this setup. Therefore, characteristic of a is not equal to 1. Similarly, what is f of 2? It is f of 1 plus f of 1, which is what? It is 1a plus 1a, which is 2 bar plus y minus x square, 2.1a. Yes, 2.1a, which is 2 bar plus y minus x square. So element here, so this 2 bar, when I'm writing this 2 bar is in Z morph 4z x comma y. And then this element, this is the expression how we write for elements in quotient ring. Okay, and this is again non-zero since 2 bar is non-zero in Z morph 4z xy. And this 2 bar also doesn't belongs to this ideal x minus y square. Okay, there are two ways. In quotient ring, element could be 0 in that certain expression when f plus, suppose it is with respect to some ideal a, then it is 0 bar if f is itself 0 or this f belongs to this ideal a. Okay, I hope this makes sense. Similarly, in case of f of 3, okay. So in case of f of 3, it is again 3 bar plus similar to 2. 3 bar is again not 0 in Z mod 4z x comma y. And again 3 bar doesn't belong to this ideal y minus x square. But what about f of 4? It is 4 bar plus y minus x square. And in this case, this 4 bar is definitely 0 bar in Z mod 4z x comma y. Therefore, the least non-negative integer where f of that m becomes 0 is our characteristic of that ring. So as suggested by Subhadeep, this is correct. And 4 is indeed a characteristic of this ring. So since we are doing this, and also we have like many, we have seen the how Macaulay 2 is used in our lectures. So I would like to show like how to define this quotient ring in Macaulay 2. So I will share my screen again. Is A is isomorphic to Z mod 4x. Okay. I minus 4. No, I don't think it is isomorphic to that. I need to check that. And I don't know at this moment. Okay. But let me just show you how to define this ring. I will get back to you. Maybe I will write that in the discussion forum if you want. But yeah, for now I will share the screen for how to define this ring in Macaulay 2 and how to check for its characteristic there. And these calculations which we did for f of 1, f of 2, f of 3 and f of 4, we will see how it works there. So let me share this. So when you search this, just a second. When you search for Macaulay 2 in Google, you get this screen for tryout. And when you click on it, it shows you this screen where you can just click on this Macaulay 2 web and you will see this. Okay, and this is how online Macaulay 2 looks like. You can also install Macaulay 2. So it is a Linux based software. So if you have like Linux installed in your PC or laptop, you can install it quickly. Okay, so we want to define this ring A mod 4zxy quotiented by y minus x square. So in order to do that, first we need to define this ring A z mod 4z x comma y. Okay, so let us call this ring to it is z mod 4z is defined like this in Macaulay 2. For z, I mean this set of integers or ring of integer, it is the symbol is zz and quotiented by ideal 4. Okay, so when this z mod 4z is written, it is the 4z is actually ideal in z, and then the variables x comma y which are given here. This is how we define this ring. And now I define this ideal I is ideal y minus x square, right? Y minus x square was this ideal. So ideal, just write ideal and it will create ideal in the defined ring B. Okay, so you will see it is ideal in B. So this is x square minus x square plus y. It is ideal generated in B. So it already considered it as ideal in B. And then we define this A to be B quotiented by this ideal in B I. Okay. And now we define this map from Z to B as we wanted. But in Macaulay 2, when we want to define map from Z to B, we write map from map B comma Z instead of writing Z comma B. So, sorry, from A, we want map from Z to A, right? So F is map from Z to A, but when we have to define it in Macaulay 2, we have to reverse the order of domain and codomain. And since we know that this map is unique, we don't have to define it. Macaulay 2 already knows what that map is, and it will be directly defined this map from Z to A. And now we will check what is f of 1. F of 1 is 1 in A. Okay. Similarly, we will check for f of 2. It is now 2 in A. So 2 plus this y minus x square, the ideal, that entire quotient element it is considering. Similarly, we will see what is f of 3 here. I hope it is visible, right? Do I need to zoom it out a bit? I'm getting error when I type a is equal to b mod I. Did you define it properly? Okay. Are you getting, when you define this b, are you able, like, could you see this polynomial ring and also this ideal of b? If your ideal defined here b is not ideal from ring, uh, uh, this ideal defined here is not ideal of the ring b, then it will give you error, because in that case it doesn't know what this quotient is. So when you defined your ideal here, could you see that it is showing that it is ideal from your ring b? And if you have predefined ideal in your terminal, no, you are getting all of that. So if you have already defined a few rings in your terminal, just write this command here, clear all. So it will remove all the predefined rings from your, cache, and you can again start or reset this here. Okay, and try again. Okay. And see, we will see f of 3. F of 3 is -1 in A, because we are in Z mod 4Z XY. So in Z mod 4Z XY, this 3 is -1. And now we will see what is f of 4. And we are getting this is 0 in y minus x square. Okay, so as it was our guess that f of 4 is a 0 is also true here, and we saw that how the elements are calculated. And you can please try. Okay, I will try to share this as well if possible. I will see that if it is possible. And okay, so this is how the rings are defined, and this map we don't need to define explicitly, because Macaulay to know what a map from Z to ring is. It is just 1 going to 1 and so on. Okay, so we'll now go back to our original screen and okay, if you have any doubt, please feel free to write it in the discussion forum. We will definitely try to solve those. Like, you are getting any kind of error in your Macaulay 2 calculations. Okay. Apart from that, Rishat, if you still feel any problem while calculating, please let us know, and we will try to solve it. And apart from that, so characteristic, let me write it for completion. That characteristic of this A is actually 4. Okay. So is this clear now how that quotient ring was defined in Macaulay 2, and also the characteristic of this ring is 4, and how we also manually also calculated this and we got that it is 4. Uh, okay, I will try to do that. Okay, I will either add those photos or write handwritten. I will write it in the notes at least. Okay. Okay, so we will move to next question now. It is question 3. Oh, sorry, question 4. That let R is equal to this K12. Okay, let me write completely. X3, X4, where K is filled. And let us call, and this A is a set of these monomials X2, X3, comma X1, X4, comma X2 square. And now again we have to pick the correct options. Could be one or many. And first one is that X1, X4 is the smallest term in the lake order. So lake order, I will just quickly define what lake order is. But for now, well, let me just write all these options. And this x2, x3 is the largest term in in the, again, lake order. So they are asking about smallest and largest term in this set A with respect to lake order. Lake order means lexicographic order. And options A is x2, x3 is the largest in in the degree reverse lexicographic order. Okay, it is also in short form. I will be writing G revlex because this is the code of, or this is the short form which is used in Macaulay to give a polynomial ring this degree reverse lexicographic order or graded reverse lexicographic order. Okay, so I won't be writing entirely degree reverse lexicographic. I will be just writing the shorthand for graded reverse lexicographic order. And my next option is that x square is the, again, largest in in the, again, G revlex order. Okay, so we have to deal with two orders right now, lexicographic order and this G revlex, that is degree reverse lexicographic order. And any guesses? If you don't know the definition, let me just write definition. Lexicographic order. So the monomials x1 power a1, xn power an. Let me just write this x1 to xn. Is greater than, with lexicographic order, x1 power b1, xn power bn. If ai greater than bi for the smallest I such that ai not equal to bi. So it is also like saying that it is equivalent to say that the first non-zero entry of this vector is positive. Okay, so that's how we can look at it. So they are asking these two terms, that x1 is x1 x4 is the smallest or not, and x2 x3 is the smallest term in a or not. So what are the three terms which we have to compare here? x1 power 0, first term is x2 x3, so x1 power 0, x2 power 1, x3 power 1, x4 power 0, and second term is x1 x4, x1 power 1, x2 power 0, x3 power 0, x4 power 1, and last term is x2 square, so it is x1 power 0, x2 square, x3 power 0, x4. So we have to compare how this ai is greater than bi whenever it is not equal to. So any guesses here? So the second term is the largest in length. Yes, it is the largest because see, this is definitely not. So they are asking whether x1, x4 is largest term in A with respect to x1. x1, x4 is the smallest. So as suggested by Shubhadeep, this is the largest because see, If this is smallest, it means that it has to be small with smaller than this as well as this. But if you compare these two, this is definitely not smaller than this one, because see, if I write this is what 1 0 and this is 1 0 0 1, and when I subtract this, it is minus 1 1 1 minus 1. Okay, so first non-zero entry is negative. Oh. So therefore, let me just write. So this is not smallest. So therefore, this x1 x4 x1 x4 is not smallest, because it is in fact bigger than this x2 x3. I hope I'm first one is smallest with respect to both g rev lex and leg. Okay, we will see that. Okay, so for g rev lex, we are not asked about this for x1 x4. So let us see. And the second term, this one, we have again, this is what 0 2 0 0, and when I subtract, it is 1 minus 2 0 0. So this is definitely greater than leg, and so therefore, as they have asked that x2 x3 is the largest, it is not true, because this one is the largest here. Is it okay? First one is not true. We will check now. This one is left, and we have to check. So this, so x2 x3 is smaller than x1 x4, right? And now they are asking about x2 square, and we have to check whether this x2 x3 is largest here or not. So we have to check this x2 x3 and x2 square. And when I compare this is 0 1 1 0, and here it is x2 square, which is 0 2 0 0, and when I subtract, it is 0 minus 1 1 0, and that's why this is less than. So x2 x3 is not largest, is not smallest, and again x2 x3 is not largest. I'm just comparing the powers. So this first one is not gone and second one is gone, because we have x2 x2 x3, which is smaller than x1 x4, and here we have x2 square, which is larger than x2 x3. So that's why. And now the third one we have to check, and here I will give definition of this graded reverse lexicographic order, and it is that this x1 power a1 xn power an is greater than x1 power b1 xn power bn if first this summation ai is equal to summation b is greater than equal to summation bi, that is degree of this element xn power an is greater than degree of this x1 power b1 monomial x1 power bn, and if this degree is equal, then what we do, we check whether this ai minus bi less than 0 for the largest I where ai not equal to bi. So equivalently, we check that the last non-zero entry. So we are talking about the largest I. So it is last non-zero entry in a1 to an minus b1 to bn is negative. Okay, we want this to be negative. Okay, and now let us check these elements here. So they are just asking which one is the largest, x2, x3 or x2 square. So let us compare this x2, x3 and x2 square. And in this case, it is 0, 1, 1, 0. Yes, x2 square is the largest, correct. So 0, 2, 0, 0. And when I subtract, here what I get 0, minus 1, 1. So see, this is positive. So we have this with respect to G Revlek. Okay, so x2 square is the largest. Even here we got that x2 square, x1, x4 is largest here, and here x2 square is the largest. Okay, is it clear? So this one is false because x2, x3 is not largest. So this x2 square is the largest one. Any doubts here? Just if you are unable, like if you can't see this, like the way I have solved, just write them properly, compare each two pair and try to solve and see that, as suggested by Subhadeep, that x2 square is the largest. Also check what is smallest in G Revlek, and similarly for these two, for lexicographic order. And again, we know that if you can also check this in Macaulay 2. You can give this monomial orders in Macaulay 2. So I will again share my screen and I will show you like how we can give this monomial orders to a polynomial ring in Macaulay 2. Okay. So let me share my screen again. Okay. Can you see this? So I'm right now clearing everything. So as I told you, right? You can clear all. So it will just clear all these variables which we have used here, x, y, and everything. Everything in the cache will be deleted from this server. So when we do clear all, everything is clear. And I will now define this polynomial ring again. So we have this polynomial ring. First, we will do with respect to lexicographic order. So how to do that? So we define this ring R. I'm defining it over rational numbers, ring of rational numbers, and variables are x1. So you can either write x1, comma x2, comma x3, comma x4 like this, or you can just write this x1 to x4 with just two dots in between. Okay, so it is shortcut because if you have 20 variables, what will you do? So this is the shorthand to define all these variables. And we wanted to define but order on this ring R. So how we do? This is the code, monomial order. And for leg, this is the symbol for leg in Macaulay 2. Okay, and this is how we define this. Is it okay? You can see this, right? The screen and everything, and also I'm audible so far. Okay, please feel free if you are unable to see anything, do anything, or if there are any doubts. And now these polynomials, I want to check, right? These were the polynomials, x1, x2, and x3. So we have to check whether this x2, x3. So multiplication is denoted, is given using this asterisk mark. We have to check whether this x2, x3 is largest. So let us check whether this x2, x3 is greater than x1, x4, and we will see. It shows it is false. So x2, x3 is not larger than x1, x4. And similarly, since they had asked about the largest, let us also check it for whether it is larger than x2 square. And again, it is false. So indeed, it is in fact smallest because it is smaller than both x1, x4 and x2 square. So x2, x3 is indeed smallest with respect to this lexicographic order. Any doubts here? Also, one more thing. Okay, no doubts. Great. And also we want to, so this x2, x3 smallest, x2, x3 smallest, which we know. Now we will compare x1, x4 and x2 square. So we will see that x1 star x4, whether it is greater than x2 square or not. And it said is true. Okay, so this x2, x3 is smallest and this x1, x4 is largest in this set A with respect to lexicographic order. So here, please note that it is with respect to lexicographic order. And we will also check this with respect to graded reverse lexicographic order or degree reverse lexicographic order, how to do it. So let me again now clear everything because now the variables might overlap. So you do not need to do this clear all every time, but I'm doing this so that variables do not overlap and we don't get any error. So let me just again define this. Let me give it a name S with again 4 variables. And now the monomial order is this G rev like. Okay, so this is graded reverse lexicographic order. And this is how it is defined. That's it. And we will check all this whether this x2, x3 is greater than x1, x4. Now it will be checking it with respect to graded reverse lexicographic order. Okay, and it is true. See, earlier it was false with respect to lexicographic order, but now it is true that x2, x3 is indeed greater than x1, x4. Now we will check whether this x2, x3 is greater than x2 square or not, and it is false. Okay, so x2, x3 is greater than x1, x4, but it is not greater than x2 square. And now we will check how x2 square is compared to x4 and x1. So see, this x2 square is neither smaller than x2, x3 and not smaller than x1, x4. So it is indeed largest among this. Okay, any doubts here? And you know how. So, and apart from this, if you want to define graded reverse lexicographic order, I will just tell you the command, though we do not have to do it for this question, but just for the sake of completion, we can define this. This command worked fine in Macaulay too. Great. Okay. You can also try the earlier commands and let me know if you face any problem. Okay. So this monomial order, and this is G leg. This is graded lexicographic order. Okay, this is the command for graded lexicographic order. So in general, something which is greater in lexicographic order need not be, I mean, the equality doesn't hold in both the cases. Okay, we can have counter examples for both the inequalities. So this is also great exercise where you see like if something is, so if two monomials A and B, if A is greater than B in lexicographic order, whether that is greater than B in graded lexicographic order or not, and vice versa. Okay, so it is good exercise to do that. And apart from that, is it okay how to define how orders in give order to polynomial ring in Macaulay 2 and how it is compared? Okay, it's not always we have to write it greater than, you can also write it less than, it doesn't matter. It will give you whether it's true or false. Okay, is it okay for now? So we will again start with this our questions. So far, I hope this was okay. So we will move to our next question. question 5, I guess. If I lambda, where lambda in this capital lambda is a collection of prime ideals, then they are saying that this intersection I lambda belong to this capital lambda. So lambda is running over this capital lambda is radical ideal. Okay, it's radical ideal. So we have to check whether this is true or not, or indeed we have to prove this. So what are your guesses that it is true or not? If not, then give me counter example, or if it is true, then we have to prove this. So any guesses whether we should try to prove this, or you have any counter example for this? Okay, I will give you the definitions of prime ideals. And so let for prime ideal, so let A be proper ideal of R, then A is prime ideal in R if AB belongs to A, then either A belongs to A or B belongs to A. So it is like if, or let me just write it for A comma B in R, if AB belongs to A, then A belongs to A or B. So if product of two elements belong to ideal, then one of the element must belong to that ideal. That is the definition of prime ideal. And what is radical of an ideal? Okay, so what is radical of an ideal? So let A be R, then radical ideal of A, or radical of an ideal A, is, it is denoted by this square root of A, and it is all those elements A in R such that A power n belongs to A for some n non-negative. Okay, so this is radical of some ideal, and an ideal is called radical ideal if radical of, right, let us me say an ideal A is called radical ideal if its radical is equal to itself. Okay, it is clear like what are the definitions. So prime ideal is when if the product belongs to the ideal, product of two elements belong to the ideal, then one of the element must belong to that ideal. And in the case of radical, it is all those element A from the ring R such that A power n lies in A for some non-negative integer n. And ideal itself is called radical ideal if its radical ideal is equal to the ideal itself. Is it okay now, the definitions? Okay, so apparently this question that given that if I lambda is a collection of prime ideals, then its intersection, and this lambda could be any index set. It could be finite, infinite, They say that it is a radical ideal. Okay, so we will try to prove this. So let me give some name to this ideal. Let me call it I. Okay, so to show this I is radical ideal. Okay, so first thing to note that for any ideal, so this statement is true for any ideal, or let me write this in some different, okay, for any ideal A, A is always contained in radical of A, because note that since for any A in A power 1 belongs to A. So this implies that A belongs to radical of this ideal A. Okay, is it clear? So in our case also, this I is anyway contained in radical of this I. So when I am saying that I want to prove that I is a radical ideal, I want to show that I is equal to radical of I. Okay, so first inequality, so that is to check I is equal to radical of I. Okay, and clearly I is contained in radical of I. So now I want to check the other way around. So now I need to check that radical of I is contained in I. Any doubts here what I have explained so far? Okay, it's clear so far. Great. So we'll start to prove that this radical of I is contained in I again. Okay, so let me choose some f in radical of I. Okay, so what does this imply? That f power n belongs to I for some non-negative integer. Okay, so this implies what? That f power n belongs to I lambda for all lambda in lambda, right? Is this clear? This is the definition of I, right? I is intersection, or let me just write this. Intersection of I lambda, lambda belongs to lambda, and this implies that f power n belongs to I lambda for all lambda in lambda. Is this clear now? Since they are prime, then it's done. Exactly, exactly. So since this each I lambda is prime, so since I lambda is prime ideal, f power n belongs to I lambda implies f belongs to I lambda. So f power n means what? F power n minus 1 into f belongs to I lambda, right? So it implies what? That either f belongs to I lambda or f power n minus 1 belongs to I lambda. So in first stage itself, if we get f belongs to I lambda, that's okay. Otherwise, we will boil down, we will like again split this n minus 1, n minus 1. And there will be a stage where it will be after finitely many steps, in fact, f I square will belong to I lambda. And this will imply that f belongs to I lambda or f belongs to I lambda. And eventually we will get that f indeed belongs to I lambda. And this is true for every lambda in my capital lambda, the index set capital lambda. Okay. So this imply what? That f belongs to I lambda for all lambda in capital lambda. So this imply what? F belongs to this intersection I lambda by the definition. So this imply my f belongs to I. So therefore, this radical of I is indeed contained in I, and therefore this I, which was intersection I lambda, lambda belongs to lambda, is radical ideal. Is it okay? Okay. So good. So just a second. Great. Any doubts, please let me know. If not, then I will move to next question. It is also related to radical of ideal. So this is, I guess, question 6. Yes. So question 6, that we need to prove that radical of a radical ideal is radical. Okay, this is quick check, but we need to prove this once at least. So any cases so we have this thing which is true for any ideal. So which one is contained in which one? That A is contained in its radical. So we already have that I is contained in radical of I is contained in its radical. Okay. Now, so therefore we need to prove the other way around, that radical of I is contained in radical of I or not. Any cases for this, that how we will proceed or how to do this? Take element then its power. So we have to do nothing, just go with the definition as suggested by Rishad. Okay, so F belongs to radical of I. So what does this imply? That F power n belongs to radical of I for some non-negative integer z, n. Okay, but once I have F power n belongs to radical of I, what does this imply? That F power n power some m belongs to I, right? This is definition of radical of I. Okay, and for some m in non-negative integers. So these imply what? The F power mn belongs to I, where this mn is a non-negative integer. So this imply what? That F belongs to radical of I, and that's where we start. So F was in radical of I, and we got that F is in radical of I. So this imply what? The radical of I is contained in radical of I, and this gives me the equality. Okay, like yes. And so any doubts here, like how it was? It was easy, but still we need to know these things because these things come handy when we do further calculations and so on. So was this okay? Yes, yes. Nth radical, nth radical. So in short, we saw that the radical of some ideal is always a radical ideal. This is what? So the radical of some ideal or of an ideal is always a radical ideal. This is something which I was trying to, which we did here. Okay, so what you said is again correct for finite steps, but this is the takeaway from this, that radical of a radical ideal is always a radical ideal, because what is this? This implies that is radical ideal, right? By definition. Is it okay? Now let us move to next question. Question 7, that true or false, every subring of a field is Noetherian. Any guesses here? So subring of a field we know. So field is always Noetherian. Noetherian means every ideal is a so Noetherianness has multiple equivalent condition when we define it. One of them is that a ring is Noetherian if its every ideal is generated by finitely many elements. Apart from that, we can also conclude this that a ring is Noetherian if every ascending chain of ideals stabilizes. So if I have, so let me write that a ring R is Noetherian. Yes. Oh, so your guess is true? So can you prove this, that every subring of a field is Noetherian? So far those who don't know, if it satisfies ascending chain condition of ideals, that is, if I1 is contained in I2, contained in I3, so on In, this is where II are ideals in R, then there exists N naught in N such that In is equal to In naught, or let me take Im is equal to N for all m greater than equal to N. And equivalently, just a second, equivalently, if A in R is ideal, then A is finitely generated. Just a second. So these are the definition of Noetherianness. These two are equivalent conditions. Let me write this here. 1 and 2 are equivalent. Okay. Apart from that, yes. So argument was given where it I mean, can you resend it? I can't see it. I guess, did you delete it? Okay. Okay. So question is that every subring of a field is Noetherian. So in case of, no worries, in case of field is always Noetherian because every ideal, the only ideals or the only proper ideal in field is 0 and the ring itself. I mean, the ring itself is ideal generated by 1 and 0 is the ideal generated by 0. And if we take any, the only possible ideals, let me write bigger, only possible ideals in field are 0 ideal and this one ideal, which is again the field itself. Let me write this F. As if we take any element A in some ideal, so if A is an ideal in F, then if A belongs to A, then A into 1 by A belongs to A, right? And 1 by A belongs to this F since F is filled. So this implies 1 belongs to A, and the moment I have 1 belongs to A, this F becomes entire ring, entire field. Okay, so only ideals are 0 and F. So field itself becomes a Noetherian ring because there are only two elements which are generated by a single element, 0 and 1 namely. So field is Noetherian. So they are asking whether every subring of a field is Noetherian or not. Any guesses? True or false? So Subhadeep said that it is true. I mean, do you still feel it is true or you want to change your guess? Or if true, then we have to give a proof. If not true, then can somebody suggest some counter example? Guesses from someone else? If not, so this is not true, okay? A subring of a field need not be Noetherian always. And in fact, subring of it need not be even field. Subring of a Noetherian ring, again, it need not be Noetherian. One example is given in the non-graded assignments, the PDF of non-graded assignment. You can go and check that. And I would like to give one example. So we can take this K, let K be filled. Okay, and we take this K, x1 to xn, so on. This is round bracket. This is not polynomial ring. This is in fact this rational functions or quotient. This is rationals of polynomials in this ring x1 to xn and so on. Is it okay? So this field has infinitely many variables. So this polynomial ring has infinitely many variables. Okay, so this is filled. Okay. And again, this G is non-zero and so on. So all this conditions which we need for this to be well defined. Is it okay? This is filled. I mean, any doubts like this is filled or how the elements of this ring look like or this field look like? Any doubts? If not, then I will move further. Please let me know if you have any doubts how the elements of this ring are and how the infinite variables thing is working here and so on. Okay. If not, then I will move. And then this key x1 to xn contained in this rational is contained in this rational field x1 to xn is subring of kx1 to xn so on. This is subring. And is this so if this kx1 to xn Noetherian, is this Noetherian? No, right? So this is not Noetherian as which is not Noetherian as ideal generated by this all the variables in k x1 to xn is not finitely generated. And if you want to quickly see the ascending chain condition, we can have this. This x1 is properly contained in x1 comma x2 ideals. Similarly, this again contained in x1 to xn. And this ring goes on. And it doesn't stop since there are infinitely many variables. We can always add one more extra variable to this. And this, the above chain does not stabilize. Okay, any doubts here? Please let me know if you have any doubt. Okay, so I assume that you do not have any doubts. Just a second. Okay. If you have any doubt, please let me know. Otherwise, I will move further and we'll try to solve next questions. And next question is on similar line. And I mean, it's not related to Noetherianness. Okay, Stabilizes means what is, yeah, stabilizes mean this, that if I have this, let me highlight this. If I have this chain of ideal, there exists n naught such that im is equal to I n naught for all I m greater than equal to n naught. So it is like this chain looks like this. That is, this chain becomes I1, I2, so on up to In naught. And then for this In naught plus 1 and so on, I mean, it just continues for every m. So it stabilizes, it becomes stationary after a time. Is it okay? So after a while, all the, can you give? Okay. Okay, particular example. So, okay, it's, so you want example where like something related to Q or Z or other file. So in case of C, Q is a field and Z which you are taking in Q, Z is principal ideal domain. So every ideal is now again a finitely generated. So we do not have so we can't have this condition because it is equivalent. 1 and 2 are equivalent. Second one is what? A is finitely generated. That is, every ideal is finitely generated. Since Z is PID, so let me just tell you. So in case of Z, you give me some ideal of your choice. In Z, can you give me some ideal? How that ideal look like in Z? So ideal in Z, for example, ideal generated by 70, if you take, what it is contained in. Can you give me some ideal which is bigger than ideal generated by 70? Okay, you went ahead very quickly. Let me just write a few elements in between. For example, let me write 35. Okay, then it is again contained in what? Ideal generated by 7. And once I have 7, it has to be Z, right? There is no, so 7. So in Z, ideals generated by prime ideals are maximal, if you know. So there is no ideal in between here. Okay, and this ring stabilizes, right? If you can't always take this ring till infinite here. For example, take any element in Z. That element has this form, right? P power m1, Pn power mn, right? And if it has to be contained in some ideal, it has only this, what I can say, finite number of choices to extend this ideal further. For example, you can just take this to be P1 power m1 minus 1, P2, Pn power mn. Am I right here? Yes, I guess. Okay. You just reduce everything and you will have this dot 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 P1 power m P1 into P2, so on P1 power mn, right? Yes, exactly. The chain should be finite. I mean, doesn't matter how many you add ideas above it. It must stabilize somewhere. I mean, you can't go ahead infinitely. You can't go ahead adding more and more ideas above that previous ideal. Is it okay now? I mean, did you understand like how this stops and so on? Okay. I hope now it's clear that what chain stabilizes mean and how you can see that in Z. Uh, Yes, exactly. It terminates somewhere. Yes. It terminates somewhere means exactly saying that there exists some n naught where all the elements above that inclusion are equal and so on. Okay, I hope now this is clear, like what is Noetherian and so on. If you have any doubt, please let me know. We will try to clear it. Okay. Rishit, is it okay? Like, okay, got it. Great. So we will move to next question. Just a second. Okay, let me just check. Question, which question number? 8. Question 8, that the characteristic of a ring is 0, then it is domain. Any guesses? So we have to check whether this statement is true or false. Any guesses for this? Domain means you know, right? It is integral domain. Okay, so if you don't know what integral domain is, a ring is a ring A is or R is integral domain if for AB in R, if AB is 0 for AB in R, if AB is 0, then A is 0 or B is 0. One of them needs to be 0. So characteristic of a ring is 0, then it is a domain. That is your guess? Okay. Can you prove this? I mean, since this is just mathematical general statement, can you give me a quick proof as you said that this is true? Others are feel free to like think other way and try to find some counter example. But since Shubhadeep, you suggested that this is true, can you give me a quick example? And also please understand this definition. If there are any doubt, please let me know. Example for this is Z, Q, and polynomial ring Kx, Kx1, 2xn, and so on. Anything. Okay? There are, in fact, I mean, there are many examples of that sort which we know. Okay? Assume that it is not domain. Okay. You are saying that suppose it is okay. So R is a ring, okay? R is a ring. So when I talk about something being domain, that ring need not even have, I mean, integers of that sort. I mean, if you know what I mean by that. So when you write this, let M n be 0, this implies this where M and n are in this ring R. M and N are elements of R. I mean, and then you are saying that Mn into 1 is 0, and but this Mn are elements of R. This need not be even integers. Now, do you understand what I'm trying to say here? Yes. So Z3 has characteristic 3. So it is like other way around. Domain which does not have characteristic 0. But we are talking the other way around. If something has characteristic 0, can we say that it is domain? Okay, so the counter example which you have given is like contrapositive counterexample. Okay. Okay, you got it, right? So can you give me counterexample where characteristic is 0 and the thing is not domain? Yeah, you were giving the counterexample of converse. Okay, but we need counterexample of the straightforward. The characteristic is 0, then whether it is a domain or not, and so on. This is absurd. I mean, this is true, but m, n are not integers here. So can't talk about, conclude anything about characteristic. Okay, if this helps. And can you give me counterexample, or at least anything which comes to your mind? Okay, forget about whether it is domain or not. Can you give me rings which have characteristic 0 at least? Z, okay, Z has characteristic 0. So can you cook up some ring where it is not domain from Z? Others, I'll feel free to please your suggestion or guesses or anything. If you get any counterexample, please let us know. Okay. QRC are also examples. Yes, exactly. QRC are also examples with infinite, what I can say. Yeah, with characteristic 0. Yes. Yes, they are. Yeah, I mean, not Z. QRC is also fine, but can you give me some, explicit ring which has characteristic 0, but I don't want it to be a domain. We take quotient ring and multiple two elements. Exactly. So that's what we will be doing. Okay. So we can take this ring R. Okay. As suggested, we will take this R to be and take this. Is this ring okay? What is that our f from Z to this zx mod x square? So this is not domain. Okay. First of all, this is not a domain. Note that R is not domain. Okay. And again, since we can take this x plus x square and multiply this with this x plus x square. What is this? This is x square plus, and which is what? The 0 in my quotient. Okay. So which is 0 bar in zx mod x square. So we have a ring which is not a domain. Okay. So R is, so above R, let me write here, is not domain. Now, what can we talk about its characteristic? How to conclude that characteristic of this ring is non-zero? Sorry, characteristic is 0. Kernel trivial, okay, kernel trivial. What is kernel? So F is this this is from Z to ZX mod x square, where this 1 goes to 1 and everything this f of n again goes to this. Let me write R here. This is R. F of n goes to n times 1 R. Okay, but if I write this explicitly, what is f of n? It is 1 plus, so let me write this 1, okay? This n times plus this x square, right? This is not equal to 0 plus x square, right? Because this, first of all, this 1 plus 1 is what? N plus x square in Z. So elements here are of this form, right? These are all f plus x square, where not f, let me write this polynomial p, not p, h, where h in Zx. Elements are of this form. So this is n. N is kind of polynomial in my Zx, and which is definitely non-zero because this n is clearly non-zero and n also doesn't belong to x square. So therefore this is not equal to 0 bar in my quotient ring. Is it okay? And this is true for any n. So this is true for any n strictly greater than 0. Okay, so therefore, as suggested by Shubhadeep, it is also the kernel of this f is trivial. That is, only element that goes to 0 is 0. So therefore, kernel f is my just trivial, that is contains only 0. Okay, so therefore characteristic of this ring are, let me just write it explicitly, zx mod x square is 0. So see, we have a ring which has characteristic equals to 0, but the ring itself is not an integral domain. Is it clear, this example? Okay, so let me just again quickly show you how the characteristic of this ring is 0 in again Macaulay 2. Let me just share the screen. And once more, I will be defining quotient ring. So those who couldn't understand how quotient ring was defined or were getting error, this is again once again I am showing how it is defined. So let me clear everything again. But you all can see the screen, right? And what I'm typing here. So let me just clear again everything. And now I am defining this ring again. Let me just call this B to be this ring ZZX. Okay. And this I to be ideal x square, which we defined here. And A is now B quotiented by this ideal I. It is polynomial ring. Okay, and you need not always write it this way. Okay, you can always define it like this also. C is equal to ZZ or QQ in that matter. Okay, ZX. And you can just write this D is equal to C quotiented by ideal x square. So you can also define it like this. That's not a problem. You don't always explicitly define ideal I separately. You can just write it in like this, and Macaulay 2 knows what you are talking about. Okay, so my A was this ring, which is quotient ring, B quotiented by that ideal. And if so, this is code for characteristic, and it shows that characteristic of this ring A is 0. Is it okay? So it clearly showed that the characteristic of this ring is 0. And now if I use this ring A, okay, so I'm just doing the calculations now in A because I also used define this ring C with the same variable x, so we don't want to mix both the variables. So I am now using A. So all the quotients and variables and numbers which I will be writing after this use A command, the calculations will be carried out in A. For example, if I write 1 here, it's showing 1 sub A. So it is 1. So see, when I wrote this 1 here, it just considered 1 from Z. But when I write this 1 sub A here, it considered this 1 of quotient ring ZX mod X square. Okay. And if I consider this X here, X is element here again. And when I take X square, it gives me 0 in A. But because what was my ring A? A was ZX mod X square. So when I do this X square, it becomes 0 in my quotient ring. So this is not a domain. So A has X has characteristic A has characteristic 0, and also A is not domain because X was non-zero and X square is 0 in my A. Is it okay so far? What is shown on the screen? And let me see what Rishad has to say. If we take matrices, then their product can be 0 even if the matrices are non-zero. I mean, matrix rings are not commutative, but can we take some? Yes, definitely. You can always have. So far we are working with commutative rings with identity. So if you get any kind of commutative ring with the characteristic 0 and it is not integral domain, that's completely fine. Here I am just giving this because we know what ZX is and how quotient ring can. But we can have multiple examples which need not be polynomial rings or anything of that sort. Yes, we can work with the matrices. That's not a problem to see that it is not an integral domain, and again it is of characteristic non-zero, but again it is not a commutative ring as you yourself pointed out. But yes, that is non-commutative ring which has characteristic 0 and also not an integral domain. Yes, definitely. If that is I hope your doubt is clear. We can generate such examples which has nothing to do with polynomials. Okay. Okay, so if you have any doubts here, please let me know how the commands are working and so far. Okay, if not, then I will just again go back to our questions. Commands are working. Great. Commands are working. So I will try to collect all those commands and add it here. Okay, if possible in the notes. And apart from that, okay, just we still have 10 minutes left. So we will try to do one more example, one more question. Okay, so let us take this. We'll see whether we can. This is question number 9. So they are saying that let P be a prime number. The intersection of all maximal ideals of ZX containing P is. So P is prime number and we are in ZX. So when it says it is containing P, it means it also contains ideal generated by P. Okay, and their question is that whether this is 0, and they are writing this something as Px, which is P into F, where F in ZX, and it is also nothing but ideal generated by P in ZX. And I'm writing it here in ZX because ideal generated by P in Z is different from ideal generated by P in ZX. Okay, and now this is something, so it is ideal generated by Px, so it is Px into F such that F in ZX. So these two ideals are different. Okay, for example, this ideal contains this Px plus P, but this ideal does not contain Px plus P. Okay, so these two ideals are different. And D is ideal generated by x power P. It is nothing but x power P into F, where F is in Zx. Any doubts here? And what is your guess? So see, this question has only one correct answer. Okay. So can you just get rid of elements, options, so that you can conclude that, okay, this is definitely not an answer. Any guesses of that sort? CD are not. Can you give me example which does not belong to C and which does not belong to D? Clearly the P itself. Okay, so we are talking about intersection of maximal ideals containing P. So, yeah, B is true, correct. As suggested by HL, I don't know their name, but so B is correct. And so now B is correct, we have to get rid of the rest three. Can someone suggest me why first one is not the answer? Well, let me just write. So this is intersection. So it is we are talking about the intersection of all maximal ideal containing P, right? So it is like, say, since it is intersection of all the ideal, it has to be ideal. So let I is intersection of M, where M is maximal in Zx and P belongs to M. Okay, so P belongs to M for every M on which we are taking the intersection, right? So this implies P belongs to I. Since P belongs to M for every M over which the intersection is taken. Okay, so clearly, so where does P belong? It belongs only to the option B. Okay, so what I wrote here, is it clear, this section? If anyone has doubt here, please let me know. So clearly, P is not contained in 0. So this is gone. Similarly, this single element P also does not contained in Px, right? Because how elements of this look like? Px into something where this F is in Zx, and we do not have anything in Zx which when we multiply we will get P again. Do you understand what I'm trying to say here? So therefore this P does not belong to Px. Similarly, P also doesn't belong to this x power P, because again we do not have any element in Fx such that when I multiply it with this x power P, I will get P back. Okay, so it also doesn't belongs to P. Let me just write it here again, which belongs to Zx. So this is also wrong, and this is also wrong. So we got that this is correct, but can you give me an argument that how this is the only, this is the correct answer? If this was not, this was all true or none true, something kind of that situation. How can you prove that this is the ideal? This is actually the ideal which is intersection of all those maximal ideals. Do you have any argument for that? That how to prove that? Like to prove I is equal to this PZX quotient with it. And when we take quotient, what we will get? I mean, how are you I mean, what will you do after taking quotients? I mean, when we take quotient with what? The entire I or with some maximal ideal M? Okay, so let me just tell you this one thing and you can check this, that maximal ideals of ZX are of the form P comma F, where F is where P is prime ideal and this F is irreducible in FPX. Okay, so this FPX is polynomial ring where coefficients are coming from FP. FP is nothing but ZP. Okay, let me just write this is nothing but ZP. So we want to, our claim is that this I is nothing but P in ZX. I'm again writing it to avoid the confusion between ideal in Z and ZX. So suppose, so if that F divided by P, so P divides that F. So suppose F in this I, then if F divides, if P divides F, then we have nothing to do, right? Because that's our claim. But suppose F in and P doesn't divide F. Okay, that P does not have any, P can't divide F. That's it. Okay. So since F is in ZX, we are working in ZX now. So F is in ZX and ZX is unique factorization domain. So we can write this F to be P1 power Q1, PM power QM, where each PIs are irreducible in ZX. Right? Is this okay? I mean, anywhere if you feel that something is not okay, please let me know. Okay, and if you have any doubt, please write it in the chat or unmute yourself and ask. Okay, so F is of this form. And since there are infinitely many irreducible elements in ZX, we can choose Q in ZX such that this Q is not equal to Pi for any I. any 1 less than equal to I less than equal to M. So these are M mini Pi. So I'm talking about those. Okay. And in that case, this P, comma Q will be maximal ideal. In ZX. But this F doesn't belong to this P comma Q, right? Because F is what? It is multiples of these Pi's and none of that Pi is equal to Qi. So this F cannot belong to this ideal. Is this understandable? That F is not in this Q? Because F has at least Pi divides Qi. Okay, and these are irreducible, none of them divides each other because they are not equal to each other. So this implies what? That Pi doesn't belong to Q. This is also one way to write since these are irreducible elements. Is this okay? And this, once we have this F doesn't belong to Q, this implies that F doesn't belong to I, which was intersection of all those ideals containing P. Intersection of all the maximal ideals which containing P, and this ideal P comma Q is ideal which contains P but does not contain F, which we chose from the intersection of all such ideals. So this is contradiction to the choice of F, okay, of F in I. Therefore, no such element is possible. Therefore, P must divide F. So this imply that F belongs to this ideal generated by P in ZX. Is it okay? Any doubts here? So we actually proved this. Any doubts, please let me know. If not, then also please let me know that there are no doubts. Okay. To the question, okay. Okay, so what we are trying to do here is question 9 that we have to, so we are talking about the intersection of all the maximal ideas which contains P. Okay, so by the method of elimination, since it is intersection of maximal ideal, it which contains P. P will be there in all those ideas, right? Because that's what we are taking intersection over. So P does not belong to this zero ideal. So that's why zero ideal is gone. Similarly, this ideal in option C is generated by P into X. Again, then just this P, the prime number P, does not belong here because I can multiply any element from ZX. I mean, there does not exist any element from ZX such that when I multiply it to this element Px, so P is not equal to Px into some F where F belongs to ZX. Okay. So therefore, this ideal is not possible. Similarly, again, P cannot be equal to x power P into F where F is in ZX. So these three ideals are not possible. That's for sure. Now we have to check whether it is this ideal or not, this second ideal or not. And that's what we try to prove here. So we consider, we started by contradiction. So suppose we take F in that intersection I'm calling that intersection to be I. I'm taking that intersection, element from that intersection, and assuming that P does not divide F. Because anyway, if P divides F, then that's what we are claiming it to be. So suppose P does not divide F. Okay, so now I do not need to explain further, or it's okay. Okay, I will just quickly go through again. So P does not divide F. So then F is of this form. Okay, F is some element which does not divide P. Okay, which is not divided by P. And then I take this. So this is because Z we can always write, every element of Zx can be written as multiplication of irreducible elements. Okay. And then there are infinitely many irreducibles in Zx. That is also a case. Okay, that is also known. So since there are finitely many irreducibles, so this F is product of finitely many irreducibles, we choose a irreducible apart from these PIs. And then we take this ideal. So this ideal is maximal here. So this P comma Q is maximal in Zx. Okay, but none of these PIs is equal to Qi, or if this PIs does not divide Q, then this maximal ideal does not contain F, right? Because neither neither P divides F or neither Q divides F. So this maximal ideal, so F does not belong to this since P doesn't divide F and Q also doesn't divide F. So this implies that F should not be in I because it was intersection of all the elements which were all the maximal elements which were containing I, but this F is not in this very ideal which is part of this intersection, which I mean this belongs to this. So let me just write here quickly. This is maximal ideal containing P. Okay. So this was maximal ideal which containing P, but it does not contain the F which we started from the intersection here. So that's why this is contradiction, because we chose F from the intersection, but we have one element from the intersection where that F does not belong. So such element is not possible, that's why. So therefore this our assumption that P does not divide F fails, and therefore P must divide F, and this implies that F must be some element from this ideal F. Okay, great. Any doubts? Further doubts? I mean, we are anyway over time. So if you have any doubt, please let me know. We can't go to next question for now. But is it okay so far? If you have any doubt, please feel free to write those in the discussion forum. And I will try to give those commands from Macaulay too with the notes. I will either handwrite it or do something, but I will try to provide that as well. Okay, so if there are doubts, please let me know. Otherwise, we can end the session here. Any doubts? Okay. Okay, I think there are no doubts. So thank you. We will have the session next week again, same time. Thank you.